Hello, scientists! Let's learn about waves and review for the Unit 7 test. In the waves labs that we did, in the first one, you could change the length of the string to make different waves. And those waves had different lengths. For example, if you made the string longer, you could make longer wavelengths like this red wave. Or if you change the length of the string to shorter, you make shorter waves or higher frequency waves. The length of the string does affect the speed of the wave. Here's a photo from inside of a guitar, and you can see that the tighter, smaller strings, which are similar to being shorter, have shorter wavelengths, where the longer strings on a guitar, or they simulate being longer because you wrap them, they're thicker and they have longer wavelengths. This is a lower sound on a guitar, and this is a higher sound. Pitch is how we hear frequency, and that high and low, what we hear is what we perceive, how we perceive the wavelength. And pitch can't be measured. Pitch is a perceived quantity. In the Doppler Effect lab, we learned that if the source of a sound is moving, the speed and direction, two things, affect the pitch based on where the person is. If the person is in the car, nothing changes. If a person's standing over here, they hear the familiar ew sound. It's higher when the vehicle is coming towards you, and lower because the waves are further apart when it moves past you. So as a vehicle goes faster and faster or increases its speed, these waves get pushed closer and closer together, and the sound gets higher and higher. That's why a bike going by you with maybe like someone talking or radio playing doesn't give you quite that same meow that a car moving really fast does. And probably if you look at this picture, you can tell whether this ball that has a noisemaker in it that is represented to making these sound waves here, is that going up or going down? And if you see here that the sound waves are pushed together closer here, you know the ball is being thrown up. Here, the ball is being thrown down because the sound waves are closer together at the bottom. They're being compressed as the ball moves towards the sound waves. This person hears a higher pitched sound and will until that the source of the sound moves by them. The speed of a wave can be measured by choosing a point on the wave and measuring how far it travels in a second. So if we choose this point on the wave, and this point is actually going to move up and down, but as the wave goes by and we watch the points go by on the transverse wave as they move, we see how many times those waves travel by us in 1 second. That's a hertz. And the speed of a wave is measured in hertz. That's cycles per second. It's not just a car rental company, it's cycles per second. This is either a transverse or a longitudinal wave, and see if you can guess. If you have a hard time remembering, transverse waves, the particles move up and down, where the wave is moving in a perpendicular direction. So if you remember that perpendicular makes a T for transverse. The particles move this way, the wave's going this way, or could be the other way around too. The wave could be moving this way and the particles this way, but they're perpendicular, and perpendicular makes a T. So T for transverse, where the particles are moving in a perpendicular direction to the way the wave is traveling. This is a transverse or longitudinal wave, and we just looked at a transverse wave, so we know this one is longitudinal. And the way you can remember that one, everyone gets along in a longitudinal way. The particles are moving in the same direction as the direction of travel for the wave. So everyone gets along in a longitudinal wave, and the particles move in the same direction as the wave. A surface wave is I gave an example of a surface wave here. Is it longitudinal, transverse, or between two different materials? If you guessed between two different materials, you're correct. A water wave is a perfect example of a surface wave. Particles in which wave move in circles? Well, you know, looking at the last picture, that this is a surface wave. And I'll explain how those particles move in circles. You've got the combination of two waves. And if you want to think of it, how would you make a circle on an Etch-a-Sketch? What would you have to use? You'd have to use the two different controls on an Etch-a-Sketch. I'll show you a picture of an Etch-a-Sketch. You would have to use the up and down control and the back and forth control to make a circle on an Etch-a-Sketch. And so it's the same kind of idea. You have to use a transverse wave where particles are moving perpendicular, and a longitudinal wave where the particles are moving back and forth. And if you put perpendicular up and down and back and forth together, you get circles. A wave is energy transmitted. A blank wave is an energy transmitted in a definite direction and with a definite speed. Here's a picture of water dripping into a sink full of water. And is that a standing, a breaking, or a traveling wave? If you said traveling, you're absolutely correct. And which kind of wave is not confined to the space along the medium? Standing, breaking, or traveling? Traveling waves, the crest is seen to progress across the medium, or like in the ocean, a wave doesn't have to stop because it runs out of water. Well, eventually it does, it runs into land, but it can keep traveling for a very long distance. It's not like a guitar string or a violin string or the string we used in lab, where the wave can only travel on that limited medium. A standing wave looks like it's vibrating in one place, and this often happens and is demonstrated with slinkies or strings. You can see this is a great example of a standing wave. This is a little bit of a YouTube video that I will put in the notes as well. You can see that the wave is just traveling back and forth within the same length of medium, and here's one wavelength. There was a half a wavelength. Now there's one whole wavelength in there. Now there's 1.5, and if they go a little bit faster, they'll be able to get a 2 wavelength standing wave in there. Perfect. A standing wave is also what we did in the lab, of course, if you did the virtual lab. If two waves with identical crests and troughs meet up and basically their graphs add, we call that constructive interference. And you can see how, like, if this was +5 and this was +5 on some graph paper, this would be +10. If the opposite things happen, they meet and they cancel each other out, this happens. And the wave gets destroyed, so it's called destructive interference. You can see here that if we take a +5 and a -5, it ends up being 0. And that happens at every point along the wave. This might be -5 and this might be positive 5, and that still adds up to 0. So the wave goes to nothing. That's destructive interference because the wave gets destroyed. Sound is a blank wave because it requires a medium to travel through. You can see some cool videos on the internet of sound traveling through oobleck, and it makes some really cool patterns. So look that up on YouTube if you have some time and you want to be entertained. It's pretty cool. It's a mechanical wave. Any wave that needs a medium to travel through, like for example sound, you can't hear sound in space because there's no medium. Instruments are grouped by, these are two kinds of instruments, and notice they both have strings. This is a violin and this is a cello. You might know that if you're a musician. Instruments are grouped by how they produce sound. Pianos are really a stringed instrument as well, or percussion depending on how you think about it. If Greg drives his car past Jeremy, who hears the change in pitch? Remember, in the Doppler effect, we talked about it's relative. The sound has to change relative to your ears. If you're sitting in the car listening to your radio, the radio is always about the same speed and distance from your ears. You are moving the same speed as the radio, and the radio is always the same distance. So Greg here sitting in the car is always hearing the radio the same way. But Jeremy, if Greg has his windows down and Jeremy's hearing the sound from Greg's car, it's going to change for Jeremy. Because out ahead of the car, the sound is being compressed and you're hearing a higher pitch, a higher frequency, and as the car goes by, you hear the and the car's frequency changes and you hear that in the pitch, a lower pitch. What changes pitch in the Doppler effect? Well, we just talked about it. See if you can guess. If you said both speed and direction, you're absolutely correct. A car's got to be moving, so it has to have a speed. And the direction, remember we talked about whether you're throwing the ball up or throwing the ball down, you can tell by how the sound waves are compressed. Waves that are closer together have a higher frequency, and we hear that higher frequency as a higher pitch. So, and as in the Doppler effect, when things are out ahead of the moving object, waves are compressed, they're closer together, and we hear that as a higher pitch. How often wave particles vibrate, or how often a wave goes by, is called what? We measure it in hertz. That's the frequency, and hertz, of course, is in cycles per second. In this kind of wave, particle displacement is parallel to the direction of travel. Everybody's getting along in a longitudinal wave. In this kind of wave, the particle displacement is perpendicular to the direction of travel. The particles go this way, the wave's going this way. So this kind of wave starts with the letter T, and it's a transverse wave. Here is an example in a slinky. The region of higher pressure in a medium caused by a sound wave, basically if you're going to squish part of a wave, or out ahead of a car in the Doppler effect, car making a sound of course, this squishing, what is that called? If you guessed compression, you're absolutely correct, and here's an example in a slinky. Here's one way to measure wavelength. You go through the middle 3 times. Think about some other ways you would be able to measure wavelength there. You can go from the very top to the very bottom, or crest to crest, or you can go from trough to trough. That's the very bottom to the very bottom. And thanks for watching. take your test and then go get some light waves outside. Thanks so much. Bye-bye.